feel or who you are. Oh, there must be more. There must be another way. There must be conscious, different things in different ways. There must be love.
And welcome everybody to another Wednesday live stream regarding CCNA. It's great to have you. I've been tweaking my office, making little things a little bit better, hopefully. So great to have you here. Our focus for this session in the world of CCNA is the concept of load balancing with spanning tree. Now, a lot of times companies are going to have, and our objectives are three basic things. Number one, I wanted to touch on STP, spanning tree protocol, to remind us how that works just briefly. And then secondly, take a look at how we can map or change the path that is taken by VLANs as they go across layer 2 network. And the reason that's important is because most of that bandwidth, a lot of it is just sitting there, not ever being used unless we manipulate it with spanning tree. So let's go to the topology and take a look at the diagram, do a quick review of spanning tree, and then we'll get right into how we can improve spanning tree by doing load balancing and having some VLANs take one path and having other VLANs take another path. So we'll use this topology right here. And let me go ahead and get out a pen. I have a pen and I'm not afraid to use it. Here we go. In fact, let me just do this. Let me bring up another layer and let me use a color like this. Let's just do a quick reminder of spanning tree. So here on this bottom left, I have a table that's showing these 5 switches. This is just a replication of those switches. So there's 5 switches here, and the switches have these base MAC addresses. Now, one of the things we discussed in our previous live stream on spanning tree was that spanning tree is going to elect a root, and that root is going to be the device that has the lowest bridge ID. And the bridge ID is made up of 3 basic parts. One, the priority value, which by default is the same on all these switches, and then the VLAN plus the VLAN number, and then the base MAC address. So in this case, the one that has the lowest base MAC address is going to be the root bridge for spanning tree. So I'd like to pause just for a moment and have you, based on this information here, these base MAC addresses for switch 1, 2, 3, 4, and 5, can you tell me by default, if we're using the default priorities, which one or ones of these, well, which one of these switches, 1, 2, 3, or 4, or 5, would be the root switch for VLAN 10 by default if these are the base MAC addresses right here for those switches? So take a moment. Think that through, and you can go ahead and type in that answer if you would in the chat. Just type in switch 1 or switch 2 or switch 3 or switch 4 or switch 5, whichever one you believe would be the root bridge in the world of spanning tree. And I'll give you just a moment to do that. Also, for those of you who have not been to the session on spanning tree we did, it is in the master playlist, so feel free to take advantage of that. It's there in my channel on YouTube. It has a whole section just on spanning tree. All right, I've got answers coming in. Mohammed is the first one that I see. Spot on. Mohammed is saying switch 1. Switch 1 would be the root bridge for spanning tree. And that's because based on all these MAC addresses, that 2 in that position right there means that switch 1 has the lowest base MAC address, which means switch 1 has the lowest bridge ID, and it would be the root. And I totally agree. Let's take a look and see. So I have this topology built. Let's go ahead and bring it up. So here's switch 1. If we do a show spanning tree. In fact, let's do this. We could do a show spanning tree for VLAN 10. That'll work. But we could also do this. We could also do a show spanning tree and just say show spanning tree root. And that'll show us all the root bridges for all the instances of spanning tree that are currently running. So let's do that. Let's do a show spanning tree. And instead of saying for a specific VLAN, let's go ahead and say show spanning tree root. Press enter. And this is saying, which is pretty darn cool, by the way. This is showing us that we have 1, 2, 3, 4, 5 VLANs, and we have 5 separate instances of spanning tree. And sure enough, the root is this guy for all of them. So it's got it's the A200. Is that the right MAC address? Hold on a second. Let's take a look at our diagram. Yeah, there we go. So the one ending in A200 is the MAC address of switch 1. So switch 1 is the root for every single one of those VLANs. All right, so why does that matter and why do we care? Well, if switch 1 is the root, let's work through what the path would be. And I'll use a slightly different layer and a slightly different color for this. Let me bring up another layer and let's use red. So if switch 1 is the root, which it is, we just saw that. If this is the root for all the spanning trees, then these ports here off of the root would all be forwarding. Those would be designated ports. So it would be designated here, and also the port going up to 0, 0 for PC1, that would also be a designated port. So far, so good in forwarding. And that's because the root switch gets to forward on all of its ports. All of its ports are forwarding away from the root, and that's what a designated port is. A designated port is forwarding away from the root. And then as we take a look at switch 2 and switch 3, all these links are gigabit. And from our discussion previously on spanning tree, switch 2 would have a single root port. That's the port that is forwarding towards the root. And so would switch 3. It'd have a root port that's forwarding towards the root. And then we have this segment here. Now, this segment here between switch 1 and switch 3, or switch 2 and switch 3, that's kind of tricky because you can only have, they're both forwarding away, or they're both going away from the root, they're not towards the root, and you can only have one designated switch per segment. So it's either going to be switch 2 or switch 3 forwarding, and so they would duke it out. And if you recall, they're going to duke it out based on cost. So switch 2 and switch 3 are going to say, which one of us has the least cost, and then that one has the least cost to get to the root is going to win. But in this case, if we take a close look here at switch 2 and switch 3, they both have the same cost to get to the root because everything's gigabit here. And so between them, if switch 2's cost is 4, which it would be to get to the root, and switch 3's cost is 4 to get to the root, then the next tiebreaker is the lower of the two bridge IDs. So if we go down here to this table, and we look at the bridge IDs for switch 2 and switch 3, we can see here the 7 right there is a lower value than C in that same position. That's hexadecimal C. And as a result, switch 2 would win that election, and it would go ahead and it would become the designated port for that segment. So it'd be designated, and that means switch 3 has to go ahead and block. Again, this is a review of the spanning tree video we had previously if you want to catch that later. Now, for the rest of this network, for this switch 1 being root, we would have, let's see, gig 3/0 on switch 2 would be designated, and that's because, well, we'll take a look at the other side of this. Switch 4 has to make a decision on which is going to be its root port. Is it going to go up to switch 2, or is it going to go over to switch 3? And because the cost is the same in both directions, switch 4 is going to say, well, I'm going to choose the path for my root port that has the better bridge ID. And switch 2 still has a better bridge ID than switch 3. So this would be the root port for switch 4. And as far as this segment here, switch 3 would be a designated port. And our switch 4 on port 2/3 would be blocking. This is this is an abbreviated fast version of our longer discussion in the live stream. So far, so good. Let's take a look at the rest of the topology. And then switch 4 would be designated ports for here. So designated forwarding away from the root. And then on switch 5, it has to make a decision. Okay, who's going to be my root port, says switch 5. And do I forward on 3.3 or do I forward on 2.2? And the type, unfortunately, the cost for coming from switch 4 is the same on both links. And the bridge ID is switch 4 both times is being sent as the same. And so the advertised lowest port priority would win. And because the port priority is all a default of 128, then the tiebreaker is the lowest sending port ID. So 1/1 is lower than 2.2. And as a result, that's why switch 5 would choose 3.3, where it heard that advertisement, as a root port, and it would go ahead and block on 2/2. All right, so spanning tree. Fun game to play. Lots of details going on, but that's how it works. And also this switch 5 would be designated on gig 00, where PC2 lives, and be forwarding there. So I'd like to pause here for a moment and play a little game. And the game I'd like to, where am I looking? Here we go. The game I'd like to play is, what would the path be if PC1, up in the top left-hand corner, was going to forward a packet, and at layer 2, that would equate to a frame, to PC2, what would the path be? And I'd like us to walk that through and then verify it by going to the interface and verifying the MAC addresses that show up. So let's do this. Based on the math we just did, the path would be like this, and I will put this in a slightly different color. Let's use kind of an orange color. So if PC1 sends a frame, the frame should go, because here's the root ports, it would go from here to here. Oh man, that's gonna look ugly. Let me fix that. Control Z, there we go. I'm gonna use a different color. I'm gonna use black because it'll be visible better. So the path would be from here to here, to here, to here, to this PC. So we'll call this path A. And that's based on how Spanning Tree calculated the layer 2 path based on our switch 1 being the root. Now we can prove that, and here's how we could do it. Over here, I've got MAC addresses. So here's PC1 has a MAC address ending in 6800. And what we should see is that switch 1 learns that on gig 00. And if this is path A that's being used, switch 2 is going to learn that MAC address on 11. And switch 4 is going to learn that MAC address on 31 over these links. And then switch 5 is going to learn that on 33. So I'll put little dots there. So we should learn PC1's MAC address here, 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 and here. And one of the reasons that I'm doing that also in this demonstration is because when I was first learning Spanning Tree and trunking and VLANs, it didn't really sink in that a MAC address from like a PC1 would be learned on many different switches as that frame traveled through many different switches. And then after all those switches learn where that layer 2 address lives, they can then make forwarding decisions based on that layer 2 address. So for fun, I propose we take this topology, we look at that MAC address, we send some traffic, and then we verify that indeed each of those switches has learned that MAC address on that respective interface. And that will also help us verify the entire path at layer 2 that frame is really taking when it goes through the network. All right, so let's do that. Let's go ahead and let's go to the live interface. Boom, right there. And let's send some traffic. So from PC1, I'm going to go ahead and do a ping to 10.10.0.11, which is PC2's IP address. And PC2 is also in VLAN 10, which is down in off switch 5. So that works. That's great. Let's take a look at where that MAC address is now going to show up. And then we can also verify the MAC here. We do a show IP on this little virtual machine. So there's his MAC address ending in 6800. So let's go look for that on switch 1. So one way of doing that would be show MAC address table. Like that. That works. But it's like, well, there's lots of MAC addresses. How can we thin that out? We could do a show MAC address table for VLAN 10, and that would thin the herd a little bit. But PC1 and PC2 are both in VLAN 10. So what we also could do is just do a show MAC address table VLAN 10, do a pipe, and then say please only show lines that include, and we could specify the MAC address that we're looking for, which is this bad boy right here. So I don't want to scare anybody off here. I just want to point out that this command is just a handy way of searching specifically on each switch for just that MAC address, and that way we can focus on, okay, which interface did this switch learn it on? So let's go ahead and do that. So show MAC address table for VLAN 10, include that MAC address and press enter. And this is saying on switch 1, I learned this on gig 00. Let's take a look at our topology. So in our topology, sure enough, right here, PC1 on the top left, it learned that on gig 00. And then if we go to switch 2, it should learn that MAC address, that same MAC address on port 1/1. And we can verify that right now by taking that same command, which I will highlight here. And let's go to switch 2 and paste it in. Oh, I didn't include my exclude. Let's fix that. Here, or my include. There's the command right there. So we'll take that, go to switch 2. And this is switch 2 saying, yeah, I learned that on gig 11, which is what we predicted. And then switch 3, it should learn this. Switch 3 is not in the path, but it also did learn the MAC address. And that's because a broadcast was sent. And the connection, if we take a look at it, the connection here between switch 1 and switch 3 that broadcast would have been forwarded down here on this link between switch 1 and 3. So switch 3, if he knows the MAC address, should have learned it on 1/3. So we can verify that as well as we go through this network. So we'll go to switch 3, give the command, and sure enough, 1/3 is it. And then if we go to switch 4 should have learned it on 3/1, which it did. And then if we go to switch 5, which is our last switch in the path, it should have learned it on port 3/3. And all that does, it just helps us to confirm what our path is through the network. So that's all we're doing. We're just confirming what the path is through the network, and verifying that the MAC addresses are learned in the interfaces that we thought they would be. Now, for the problem, check this out. If that's our path for VLAN 10, and we haven't tweaked anything or changed anything, that's also going to be our path for VLAN 1 and VLAN 20 and VLAN 30 and VLAN 40 and any other VLANs we have if we're trying to go from switch 1 down to switch 5. And this path here, I'll go ahead and put this slightly different color. This path here, that goes from switch 1 to switch 3 to switch 4, that bandwidth right there, it's not being used. So it doesn't make too much sense to put all of our eggs in one basket, because we're having half of our, several links that are absolutely not being used. And we can verify that by going back to the interface and just doing a show VLAN or show spanning tree we'll show the root bridge. And this just confirms that, switch 1 with its base MAC address there, part of the bridge ID, it's the same root bridge for all those VLANs, these 5 different VLANs. So what we can do to solve that is, here's what I think. Because we have 5 different instances of spanning tree all running, they're all communicating and everything else, with rapid spanning tree and the older traditional 802.1d as far as Cisco's implementation of it, which is per VLAN spanning tree, we could go ahead and simply tell one of the other switches, like maybe switch 3, that it's the root for spanning tree for VLAN 20 or VLAN 40. And then for those VLANs, the traffic would go down that path. So we could have VLANs 10 and 30, for example, go one path, and VLANs 20 and 40 go another path, just by manipulating which switch is going to be the root bridge for those other VLANs. and because we're already running spanning tree, there's not a lot of overhead. All we're doing is simply carving out who's going to be the root for a specific VLAN and choosing the specific switch we want to be that root. So let's take a look. And here's what I propose we do. I propose, as I get a new color out and a new layer. There it is. All right, I propose, and we'll use blue for this. I propose that instead of using the same path A for everything, that we carve out a path B that some of our VLANs can use. So if we have PCs, and then let's go ahead and we'll call that path B. Now, to use path B, what we could do is, instead of having switch 1 be the root for everything, we could have switch 3 be the root bridge for, and let's just pick on VLAN 20. We could have switch 3 be the root for VLAN 20. Now, here's the interesting thing, at least I find this very, very interesting, is that once we tweak or modify the spanning tree, the physical topology doesn't change, but logically behind the scenes, we are absolutely causing different traffic patterns based on who is the root for a specific VLAN. So in this discussion, let's go ahead and make path B, we'll make switch 3, as I look at it, switch 3 the root for VLAN 20, and then let's go ahead and calculate, if we do that, calculate the path from a PC that's in VLAN 20 as it communicates with another PC, PC6, in VLAN 20. So if this guy is a root, let's play the game called who's forwarding and who's not, and what role do you have? And it goes something like this. Root bridges, they get to forward on every port. And when you're forwarding away from the root, that's referred to as a designated port. So if switch 3 is the root for VLAN 20, then regarding VLAN 20, this port would be a designated port. 1/3 would be a forwarding designated port. 2/1 would be a designated forwarding port. Great. And then if it had access ports also in VLAN 20, it would be designated for those as well. And then we go to all the losers. What do you mean, Keith, losers? Well, a loser is a switch that didn't win the spanning tree root election for a specific VLAN. So here, as we talk about VLAN 20, All the other switches, except for switch 3, are the losers. So all the losers have to identify one and only one root port. That's the port they're going to use that has the best cost to forward traffic in the direction of the root bridge. So root ports, forward towards the root bridge. Designated ports, forward away from the root bridge. And so on switch 1, if all these links are gigabit, which they are, this would be the closest cost. This would be the least cost right here, and that'd be a root port, forwarding. And let's put in our root ports first. And on switch 2, that'd be a root port, forwarding. And on switch 4, this would be a root port, forwarding. Now, up here, based on which of these two switches is going to be designated for this segment, switch 1 has a lower cost. Oh, wow, check it out. This is great. This is a very, very good discussion. So switch 1 and switch 2, they both have the same cost to get to the root. So their cost is going to be 4 each because they're only 1 gigabit link away from the root. So when they duke it out and say, who gets to be designated for this segment, switch 1 and switch 2 are both saying, my cost is 4, my cost is 4. Yeah, it's a tie. We get it. So the next tiebreaker is, if the cost is equal, the next tiebreaker is who has the lower bridge ID. So let's take a look at who has the lower bridge ID in this topology. Switch 1 has a base MAC address ending in 28A200, and switch 2 has a base MAC address ending in 72. So switch 1 has a better base MAC address, which makes it a better bridge ID if all the priority is set to equal. And as a result, for this segment right here, switch 1 would be the designated port. It would get to forward, and switch 2 would say bummer. That's how you spell bummer with an X. It would be blocking because you can't have every non-root switch gets 1 root port exactly, and every segment gets 1 designated port exactly, and then everything else is going to be blocking. So if we go down to switch 4 and switch 2, we have the same scenario. Switch 4 and switch 2 both say, hey, regarding this segment between us, we have a problem. We need 1 designated port, and they start to compare their cost. Switch 2 says, I have a cost of 4 to get to the root. Switch 2 says, I have a cost of 4. Switch 4 says, I have a cost of 4 because everything's gigabit. And as a result, what they'll do is they'll say, well, that's a tie, so who has the lower bridge ID? So then we go to switch 2 and look at its base MAC address as part of its bridge ID, which is 72 here, and switch 4 is 40. So here, switch 4 has a lower bridge ID than switch 2, and as a result, this port right here would be designated and forwarding, and this port on switch 2 would be blocking. And then going over to the right, that story doesn't change. Designated, designated, both forwarding, and switch 5 is going to choose the path with the least cost. They're equal. It would then choose based on the lowest bridge ID. Switch 4 is advertising the same bridge ID for both of those ports, or both those segments, and then it boils down to the lowest advertised port ID, which is a combination of the port priority, which is the default of 128, and then the port ID. So 1.1 looks better to switch 5, so it would be root port here, and then it would be blocking here. And then on this port 0/1, switch 5 would be a designated port that goes out to PC6. And switch 1 up here would also be a designated port for that as well. Now, if we did that, the path that should be taken then, if we follow the trail here, would be this, and I'll put it in a nice yellow color. This would be the path, our path B. And it's going off that top link there. All right, so if we made switch 3 the root bridge for spanning tree for VLAN 20, traffic for VLAN 20 off of switch 1 going to devices in the same VLAN switch 5 would be using path B. And that, my friends, is how we do load balancing. That's the concept of how we can do load balancing in spanning tree, by simply manipulating, controlling which of the devices is going to be the root bridge. So let's do that. Let's go to switch 3 and make it the root for VLAN 20. So we'll go to our interface and we'll go to the right switch, which is switch 3. Oh no, there we go. Oh, I thought it was going to lock up on me. I was like, no, I want a demo. All right, let me tuck switch 3 back in there where it needs to go. Right there. All right. So here in switch 3, let's do a quick show spanning tree for VLAN 20. I just want to make sure that it's not the root. So for VLAN 20, this device has a root port. It's not the root bridge. We can also do a show spanning tree root. That'll also confirm that switch 3, which has the base MAC address ending in 4400, is not our root bridge for anything. It's still switch 1. So we have a couple options here to control that. We'll go into configuration mode, and we can do spanning tree. And we're focusing here on VLAN 20. So we'll say spanning tree VLAN 20. And then our options for modifying that would be, we could give it a better priority, something lower for VLAN 20 than 32,768, because VLAN 20, it added 20 to that. So we could do that, or we could just say spanning tree VLAN 20 root primary. And what that does, it is a fun little game. What happens is this switch 3 says, I know what the root bridge ID is for VLAN 20. I'm listening to those BPDUs. I know what it is. And what I'll do is I will lower my value in the priority, and I'll win. So we don't have to know exactly what it is, the current one, because the switch does, and it will change the priority to a lower value, and it'll become the new root. So let's go ahead and do that. We'll press enter, and then if we do show spanning tree root, check this out. VLAN 20. Look at that. Look at that. The last 4 digits of the bridge ID, which is based on the base MAC address. It is now the root for VLAN 20. And as a result, our path through the network should now be this one for VLAN 20. And we can verify that by going to PC2 right here. And on PC2, if we look down at our table, PC2 has a MAC address ending in 6801. And let me change my color there. Right here, 6801. So if this is the path that's being used, we should find that MAC address in the path. I'll put little dots there. We should find it on gig 01 on switch 1 for VLAN 20. We should then find it here on 1/3 on switch 3. We should find that MAC address here on 2/3 on switch 4, and on switch 5 we should find it on 3/3 based on that path. And that would also confirm the path that we're literally taking as we forward unicast frames through this network. So let's test it with that MAC address in mind, ending in 6801. Let's go to PC2, which has the IP address of 10.20.0.20, and we'll ping PC6 on the other end of the network at 10.20.0.21. And we'll hope it works. And if not, if it doesn't work, we'll turn this into a troubleshooting exercise. Either way, it's going to be freaking fantastic. Okay. So let's go to PC2, and we'll do a show IP on this device just to verify its MAC address, sure enough 6801, and then we'll do a ping out to 10.20.0.21, which is PC6 on the other end of the network, and that works, so that's a good sign. Also, these times I have an emulated environment, so you normally at layer 2 forwarding with hardware, it'd be very, very, very fast. In any event, we have our connectivity, and now let's go find the MAC address. So we'll go to switch, we'll start at switch number 1, and we'll hit the up arrow key, and we are looking, I'm going to modify this a little bit. We're looking for MAC address 6801, and we want to include VLAN 20. So this is showing up on gig 01, which is perfect. I will take that command, and let's go ahead and peek at switch 2. Now, as we take a look at our topology, switch 2 should not be learning this MAC address on 1/1 because it's blocking on that port. So even though switch 1 might send frames, and it will, down that port, switch 2 is not going to be processing or interpreting user frames. So switch 2 should learn about that MAC address of PC2 on its gig 2/0. That's where we'd expect to see it. So even though it's not in the path for this unicast traffic, PC2's initial broadcast when it did an ARP was sent to everybody in the VLAN, and that's why switch 2 would have learned it on 2.0. So let's go to switch 2, and we'll right click, and there it is, 2.0. Fantastic. And then let's go to switch 3, and we'll look at the topology to confirm where on switch 3. So switch 3, we'd expect that to be learned, PC2's address to be learned on 1/3. So we'll cross our fingers there. Perfect, 1/3. And then on switch 4, we'd expect that to be learned on, and taking a look because my memory is not that good anymore. So switch 4, we'd expect it to be learned on 2/3, right there. So we'll go ahead and try that out. And perfect. And then on switch 5, I remember where that one is. That one is port we'll look anyway. So on switch 5, we would expect it to learn that on port 3/3 because that's its root port. So we'll go ahead and there it is. I just wanted to confirm that indeed it is showing up exactly where we thought it would on each of the switches. Now that does a couple things for us. It's a little bit sneaky. One is I wanted to confirm with you about spanning tree and how it elects root, and then we have designated ports flowing away from the root, and we have on the non-root switches we have one and only one root port, and then we have one designated segment for each network segment. So there can't be two designated ports. If we have two ports that want to be designated, they duke it out. Whoever has the lowest cost wins. If the cost is the same, whoever has the lowest bridge ID wins, and that pecking order has been reinforced here. So we then took a look at all the ports for how the path would be. We then changed the spanning tree root for VLAN 20. We made switch 3 be that root, and then as a result, the path B was being used, and then we traced that MAC address from PC2 all the way through the network. So let me check my notes. Number 1, I wanted to review with you about some basic spanning tree. Mission accomplished. Number 2, I wanted to verify in the path where the MAC addresses would be learned based on the path that was being used. And third, we wanted to solve the problem of having all of our VLANs. If we had 100 VLANs, by default, they're all using the same path every single time because we have by default, one root bridge for all the VLANs. So in Cisco's implementation of spanning tree, Cisco implements the basics, which Cisco sees it as IEEE. If you do a show spanning tree, it shows IEEE, but what it really is per VLAN spanning tree with a separate instance of spanning tree for each and every VLAN. For convergence issues, we then go to something called 802.1W, which is rapid spanning tree. And it converges better, has some of the tips and tools that the Cisco enhancements brought in, like backbone fast and uplink fast and some faster convergence and agreements between devices. And then, although we're not going to focus on it here in CCNA, I did want to make you aware that if somebody has 100 VLANs, and we only have a couple different paths we want to take, do we really need like 100 separate instances of spanning tree all running over and over? It's like needing 2 apps and running 100 apps just because that's the way it works by default. So to solve that, we have an option called multiple spanning tree. And with multiple spanning tree, we run 2 or 3, however many instances you need of spanning tree. And then we just say, hey, VLANs 20, 30, 40, 50, 60, 70, you all use this instance. And they say, great. And so the routers have a lot less workload because they may have 2 or 3 or 4 instances of spanning tree instead of 100. And then we just tell the switches which VLANs are going to be using which instances, and it's good to go. So come see me in Encore for all that, and we'll talk about that in detail. And that was what I wanted to cover today. I wanted to talk about load balancing with spanning tree, and we've done it. So here's what I plan to do. I'd like to go ahead and close off the stream, but for those of you who are here live, I'm going to go ahead and stick around, and we can do some Q&A. So I'm going to play some closing music, but please don't go away if you want to chat. And you can catch the entire playlist on YouTube by simply going to my page, and you can go ahead and just go to the master playlist, and I put all the videos there step by step, so they're in order. So whether it's Subnet Saturdays, or whether it's our streams on Wednesdays or Sundays, I put them in the playlist so you can enjoy them there. Yeah, so enjoy those, and I'll see you in just a few moments for some Q&A if you have it. And as always, I really appreciate your participation, you being here, and I'll see you in the next video or live stream coming up soon. Thanks, everybody.
What you're putting in, all your hopes and efforts are all in vain. Who will pick you up when you've lost everything?